G'day! Today, let's have a bit of a philosophical discussion. Because we've been talking about chance and probability and so on, and even answered some questions about it. But do we really know what we're talking about? What do we actually mean by chance, by probability and so on? It's actually kind of subtle. When you start thinking about it, something deep is going on, something mysterious. For example, think about even this object. Here's a coin. We like to say that in flipping a coin, there's a 50% chance of seeing heads. Okay, what does that mean? What does it mean there's a 50% chance of seeing heads? I mean, I'm going to flip this coin. Here goes. Flip it. Oh, and I actually saw heads. Oh, I actually saw heads. My one whole flip, all 100% of what I did was heads. So what does 50% mean? Okay, then you realize, okay, this is a statement not about flipping a coin just one time. It's actually about flipping a coin many times. All right, so I'm going to flip this coin many times, see if I understand what that 50% means. In fact, I'm going to flip this coin 10 times. Actually, no, I won't do that. What I've got instead, here I've got 10 coins, which I'll each flip once. So flipping this one coin 10 times is equivalent to flipping each of these 10 coins one time. So what I'm going to do is I'm going to drop these coins on the table, make a bit of a noisy mess, and see what happens. So this 50%, what does that mean? What should happen when I do this? Does that mean 50% of my results are going to be heads and 50% is going to be tails? Do I expect to see 5 heads and 5 tails? All right, let's do it. Let's find out. The only way to find out is to do it. All right, dropping these coins. Here goes. Don't lose them on the table. Whoop, whoop. Okay, we're good. We're good. All right. That was pretty random. They bounced around. You probably didn't see any of that. But let me just give you the results. So we have tails, tails, heads, 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 tails, tails, and tails, tails. All right. Oh, did you keep track of that? That was 4 heads, 6 tails. 4 heads, 6 tails. It wasn't 5 heads, wasn't 5 tails. It wasn't 50%, 50%. We got 40%, 60%. We didn't see that. So what's going on? What does that 50% actually mean? Well, you might argue, okay, maybe 10 was too small. Maybe I should have flipped 100 coins. Maybe I should have done 1,000 coins, maybe 1,000,000 coins. Because we like to believe that if we did more and more flips, we'll be closer and closer and closer to seeing 50% heads, 50% tails. Somehow, in our brains, we feel there's an inherent number in this object, this coin, that's 50%, that if we did a really, really, really large number of flips of this thing, then we expect to see something really close to 50% being heads and 50% being tails. We might not see it with smallish numbers like 10 flips or 1 flip. We won't see it with 1 flip. Did not see it with 10 flips. Might not see it with 100 flips. Might not see it with 1,000 flips. But the more flips we do, the closer and closer and closer to what we do see is to this magic number 50%. So this is a bit of a mind game. We like to believe there's a number 50% associated with this object. In fact, we do that with many simple actions. We like to believe in rolling a die, roll a die, there is a number associated with the action of rolling a 6, namely 1/6. Because we like to believe if I rolled a die a large number of times, about 1/6 of those results will in fact be a 6. And the more and more rolls we do, the more and more, the closer and closer we'll be to seeing exactly the fraction of 1/6 of them being the roll of a 6. Now that's a mind game, something that we believe in our heads. And we do it all the time with all sorts of simple actions. Like you have a spinner, like you spin something. We like to believe spinny things will land in certain positions based on the size of the wedges. So we associate numbers with the size of the wedges, chances of seeing a particular result on a spinner. All right, so that's what I want to write down. I'm going to clean the board and try to write down what I just said. It's going to be a bit tricky, but let's see if I can put it on the board succinctly, because if it's written on the board, then I'm being very clear about what we're choosing to believe. So we believe, here goes. So you're going to get my terrible handwriting. You're going to get some squeaky marker, because I think this microphone picks up the marker very well, so I apologize for the squeaks. So what do we believe? In performing an action, we like to associate a number, I'll call it P%. For coins, we like that to be 50%. For rolling a die, we like that to be 16 2/3%, 1/6, and so on. We associate a number, which means if we perform the action a large number of times, bad handwriting, then I'm going to be honest, about P% of the results will be the desired outcome. All right, so my handwriting is atrocious. I said about 50% for coins will be coming out. In fact, this is what happened here. When I did the coins, I actually got 40% and 60%. That's kind of close to 50%. So about is correct. But, there's more than that. If we did more and more and more, so doing more and more experiments, doing more and more runs of the action gives us results closer and closer to P%. All right, so if I did an action and I collected a large amount of data about it, we like to believe the amount of data that gives you the results you want is getting really close to P%. And the more times you run that experiment over and over and over again, the more data you collect, the closer and closer you'll be to P%. So mathematicians give this principle a name. They call it the law of large numbers. So we like to believe that actions, objects have natural numbers associated with them, P%, which tells you about the data, and also backwards. It works backwards. Data will tell you, give you some indication what this number P is. For example, if I flipped a coin 500 times, and it turns out my data gave me 403 heads and 97 tails, you say, hang on, there's something fishy about that coin, because we don't believe that. In fact, this data might be suggesting to me that this coin here is actually biased. It's going to land heads more often than tails. In fact, we might even say about 80% of the heads, of the flips will be heads, 20% tails. So we might say the probability for this coin landing heads is now 80%. The data suggests the number should be 80%, not 50%. So it works both ways. You might believe this coin's unbiased, so you associate the number 50%, in which case we expect something close to 250 and 250, or given some data, the data might tell you what percentage to work with. Got that? So just being very honest, we're actually playing a mind game here in this probability story. We like to believe there are natural numbers associated with simple actions. All right, so let me just erase this board because we've been doing garden paths to get to those numbers, but let me actually think more about law of large numbers. Let me show you how to think about probability by actually looking at data, actually choose a large number and imagine in our mind's eyes what we expect to happen and let that data indicate answers to probability problems. But I need to clean the board, so I'll be right back. Okay, so here's a standard probability problem. Imagine rolling a die, and imagine flipping a coin. Flip. So there's an experiment that has two parts, a double-barreled experiment. Roll a die and flip a coin. What are the chances of seeing a 6 followed by a head? Now we can definitely do a garden path for this. Roll a die, split 6 ways. Some will go to the want house, some will go to the don't want house, and then those that survive flip a coin to split into heads and tails. We can answer it that way. But let's use the law of large numbers in our minds to answer it a different way. So let's imagine doing this experiment a large number of times. Now I'm going to choose a number that's probably divisible by 6 because I've got die involved and I've got like heads, which are evens and tails. So I'll do a large even multiple of 6, which is handy because actually all multiples of 6 are even. So let's imagine doing 600 runs of the experiment, 600 runs of this double-barreled experiment. Roll a coin, roll a die, flip a coin. Roll a die, flip a coin. Roll a die, flip a coin, 600 times. All right, so when we do 600 runs of the experiment, we expect in rolling a die, in this ideal world, that 1/6 of them will actually land 6. So that is, 100 of these will give the answer 6 on the die. All right, so of all these double-barreled experiments, we expect 600 of them to have a 6 on that roll of the die. But then, of those 100 experiments, this is a pretty large number. We can actually do the law of large numbers there because when we're going to flip a coin for these ones, we expect half to be heads, half to be tails in an ideal situation. Or if we did bigger numbers, we'd be getting closer to half and half. That is, we expect then half of these to have the 6 for the die, followed by the head for the coin. That is, 50 out of our 600 runs of the experiment should give me a 6 and a head. So we like to believe that the chances are, given by this data, should be 50 out of 600, that is 1/12, which is exactly what the garden paths would show if you chose to do this with a garden path, which is great. Just to make one little point before we go on to a much more complicated example, the standard notation in probability theory for probability results is the capital letter P. So we just worked out the probability and they use parentheses and some little description here. So we got 6 followed by head, so probability of 6 and then head. That's how I'm going to write that. The probability of getting a 6th in the head equals 1/12. So the standard notation in probability theories use a big capital P, parentheses, and some descriptor of what outcome you wanted, and then there's the chance of getting it. Alright, so that's the law of large numbers in action. Imagine doing a large run of experiments and seeing what the ideal situation would be that inform the probabilities, or you can go garden paths, all is good. But let's now do a really complicated example and show the power of thinking about large numbers. Back in a moment, got to clean the board. Okay, here's a very complicated example, but I actually love this example because it illustrates something profound about real life. Okay, it goes as follows. A bag contains 8 Tuscan sunset orange balls and 2 Tahitian sunrise orange balls. Confusing already? The color difference is very subtle. And in fact, only 70% of the people can correctly identify the color of a ball when handed one of either color. Give the person a ball, they say, oh, that's Tahitian sunrise. They'll be correct 70% of the time. Or, oh, that's Tuscan sunset. They'll be correct 70% of the time. So we'll assume that's a fact about this color difference. So Lulu, your friend, has this bag, 8 Tuscan sunset, 2 Tahitian sunrise. She pulls out a ball at random and tells you over the phone, I'm holding a Tahitian sunrise ball. So you can't see it, all you hear is what she said. She says Tahitian sunrise. My question is, what are the chances that the ball she holds in her hand truly is Tahitian sunrise? Okay. Very different shades, it's very subtle shades of orange here. They can only be identified correctly 70% of the time. So how do I analyze the fact that Lulu says Tahitian sunrise, and is she actually right? Is it truly Tahitian sunrise? So what I'm going to do is the law of large numbers. Imagine going through this process a large number of times. In fact, let's do it, say, 1,000 times. Let's run through this with Lulu 1,000 times, 1,000 runs. Let's assume that she doesn't get better at telling color differences over 1,000 times. That's always 70%, 70%, 70%. That seems natural here. All right, so let's see what can happen. So she's going to do this 1,000 times. So there's a bag with 8 Tuscan sunset and 2 Tahitian sunrise. So there's a 8 in 10 chance she'll pull out Tuscan sunset, 2 in 10 chance she'll pull out Tahitian sunrise. So of these 1,000 times, we expect, let's color, 8 out of 10 of them, that is 800 times, she will actually pull out Tuscan sunset. And 200 times, the other 2 out of 10 times, she actually pulls out Tahitian sunrise. All right? So just following this data, it seems like that's following the setup, that's the data we should get in an ideal circumstance. If we made more runs, it'd be closer and closer to being that proportion. All right. Now, the question is, what does she say? Because there's a second stage to this process. She pulls out the ball, but then she says something about the ball. So if she's in one of these scenarios of having pulled out a Tuscan sunset ball, she'll identify it correctly as Tuscan sunset 70% of the time, and incorrectly, and say Tahitian sunrise 30% of the time. So let's get that down on the board. There's a different color. So 70% of those 800 times, 7 times 8 is 56. So 560 times, she says Tuscan sunset. She's correct and is correct. Whereas the other 30% of the time, which must be 240 of them, she says Tahitian sunrise, and is incorrect. All right. So I'm just collecting the data, what do I expect from the second stage of this experiment. And ditto for these other 200 pieces of data, where she actually pulls out Tahitian sunrise, she'll be correct in saying Tahitian sunrise 70% of the time, incorrect 30% of the time. So 0.7 of 200, there must be 14, so 140. She says Tahitian sunrise and is correct. And the other 30% of the time of the 200, which is 60 of them, she says Tuscan sunrise and is incorrect. All right, so there is the breakdown of all the data for 1,000 runs in the ideal situation. All right, now the question. So she says Tahitian sunrise, what are the chances she actually is holding Tahitian sunrise? So she says Tahitian sunrise. So where in the scenario would she say Tahitian sunrise? Well, she says Tahitian sunrise there, these 240 times, and she says Tahitian sunrise there, those 140 times, and they're the only time she says Tahitian sunrise. And look, out of this data, she is incorrect these 240 times. That's not actually to see Tahitian sunrise, but she's correct these 140 times. Okay, so out of these, 140 plus 240, that's 380 times. She's going to be correct 140 of those 380 times. So the data here is suggesting the chance of it being correct, so the probability that Lulu is correct, probability that she's correct, is actually, according to this ideal data, 140 out of 380 times. Oops, 380. That's about, that's just under what is that? That's under a third. So that is pretty low, actually. So what is that? It's 14 out of 80, 38. That's 7 out of 19. 7 out of 19, that's really low. 7 out of 19 is about 37%, I'm guessing. 37%, something like that. I could be a little bit off. But that is amazing. The chances that Lulu is correct is only about 37%. That to me is amazing because this says something profound. Look at this number here. This says most people are pretty good color tellers. They're going to be correct most of the time. 70% of the time they'll tell the color correctly. It's like being an eyewitness in a court case. Eyewitnesses are tested. How good are they at identifying colors of cars or recognizing people's faces? And they might test really good identifiers. But put them in a complex situation like this, where they have to do something with that identification probability, and look at the final result. It's pretty low. Lulu's pretty good at identifying colors, but in this scenario, the probability that she's actually right, despite that high number, is low. You cannot actually trust eyewitnesses that well. You have to be very careful of eyewitness data in court cases. Even though they might be good eyewitnesses, the actual probability you get for the whole complex scenario could still be low that they're actually correct. That's mind-blowing. This is fabulous about probability theory. So I love this interplay here of law of large numbers. Do a large number of runs, analyze the data, and see what the data says back about the probability. This is grand stuff. Fabulous.